how do we then take that observation that we just had about the distribution of these particles where there's no change in energy to actual particles that are moving around that have energy distribution and how the energy is distributed at different quantities? So in order to do that, I'm going to discuss a little bit the idea of kinetic energy distribution in particles. Okay, so the first thing is just to kind of understand that there's three different types of kinetic energy that we see in molecules. We have translational, rotational, and vibrational, and they're illustrated here on the right. So translational is just when particles are moving from one point in space to another point. As shown right here. This is rotational motion, which is, as you might imagine, it's just rotation around the center of mass of the molecule. And then this is vibrational, and that's usually motion along the bond of the particles. So it might be a stretching of the bonds, it might be pulling, or it might be bending of the bond. Okay, the reason those motions are all important is because the bending or the translation or the rotation, they're not happening on a continuous scale, right? So if you remember in Chem 11, we had discussed that microscopically energy is quantized. And the word quantized just means that the energy can only have specific value. You can't have sort of a continuous range of movement. There's certain movements that are allowed and certain movements that are not. In Chem 11, we have discussed it with respect to the location of electrons in an atom. If you remember this particular picture from Chem 11. So we have a nucleus in the middle, and then these circular tracks right here is what we call shell. And these are locations where electrons could be found in an atom. And except for those specific lines, right, we can't really find electrons anywhere else. So the electrons are forbidden from the parts that are white in that drawing. These kinetic energy of motion, all these three motion, their energy is similarly distributed along various energy levels, okay? So, for example, translational energy, you can have this different motion, okay? Different energy level. Rotational is this one, vibrational is this one. So there's specific type of vibration that are allowed, something that corresponds to this value of energy. Specific rotations are allowed, but again, only the ones that are located in these energy levels here. Now, I want to talk about this because I want to connect that idea of microstates and macrostates that we talk about to how we view the distribution of kinetic energy in a molecule. So let's take a look here at an example. Okay, so this picture here represents a distribution of all the outcomes that are possible if you have 6 identical particles that has a total of 9 energy units. So the idea here is I'm trying to take 6 particles and somehow distribute them at these various energy levels. Each one of these lines here correspond to an energy value from 0 to 9. And I want to place my particles, which are the red dots, in such a way that I get a total of 9 energy unit in the end. Okay, so one possibility is this picture number 1, all 5 particles with energy level 0 and one of them at energy level 9, right? So that's that's one way I can distribute my particle. If I do that, then I get a total energy of 9, right? Because it's 9 times one particle plus 0 times the other 5 particles, okay? Now, because the 6 particles can be considered unique particles, if we put 5 and 0 and 1 and 9, we can, change them around, right? So there's 6 different ways of having this type of an outcome, okay? Because there's 6 different particles, we can change them around. So in other words, this picture right here that I have, this is one of the macrostates that I might have, right? Which is 5 particles in 0 energy, 1 particle in 9 energy. And there's 6 microstates for that macrostate. Okay, what's another way I can get a total of 9 energy with 6 particles? Well, picture number 2 is shown right here. In this case, I have 4 of my particles have energy of 0, 1 of my particle has an energy of 1, and 1 of my particle has an energy of 8. Okay, if you look at this particular macrostate, turns out there's 30 different ways you can make this happen. Okay, just arranging those particles in different ways, but always keeping 4 having energy of 0, 1 having energy of 1, and 1 having energy of 8. So in other words, there's 30 microstates for that second macro. And I don't want to go through all of them, but in total, if you count this, there's 26 macrostates, okay? Each macrostate has a specific number of microstates as shown there. Now, what is the most likely outcome of this collection of particles? What am I going to see if I were to run an experiment where I have 6 particles, I put them, and the temperature is such that the total amount of energy that these particles can have is 9 units of energy? Well, as you might imagine, the most likely outcome is the one that has the most number of microstates. So which one has the most number of microstates? Well, there's a few of them. All of these have 180 microstates. They're possible. So those 5 macrostates would be the one that I am most likely to see. Now, which specific one am I going to see? Not any particular one. They're just going to randomly fluctuate, right? Because again, these are particles, right? They're just randomly moving around. So I'm going to see any one of these 5 just interchanging as the particles are moving around. And that's kind of how we actually take that example about the micro and macro states that we learned about that distribution of gas particles and connect to the distribution of particles that actually have some energy. Now, we're not going to ever see the macro state that only have 6 microstates. Why? Because think about it. This one has 180, that one only has 6. So the likelihood of this one is 30 times more, right? If you think 180 divided by 6 is 30. So it's 30 times more likely that you will see something like this than you will ever see something like that. Okay? One of the interesting things with this particular experiment is if you look carefully at the macro state that only has very few members, which is just that one and this one right here, with those things, you can see that they're really making all the particles kind of stay in one of the energy level and another one on something else, right? So this one looks very similar to that, which is that all of them have to be packed into that state, and then one is here. Whereas if you compare that to the macrostates that have the most number of microstates, look at this one right here. This, and then this. Those particles are pretty widely distributed. In other words, they occupy several more energy levels compared to the ones that has fewer microstates. And again, I want to connect this back to that idea that we have talked about at the very beginning, which is that idea of order and disorder. Okay, so we had said before when we look at some of these reactions that we say, hey, it looks to us that the more ordered something is, the less likely it is, or the less spontaneous that process would be, whereas the more disordered it is, right, the more likely that the system will end up in that state. Okay, making that process spontaneous. We can actually see it in this particular picture because these 5 macrostates with 180 microstates each, the ones that I circle in yellow, they sure look more disorganized, more disordered, right? Compared to the blue ones, the one that I circle in blue, that have fewer microstates. Because the one that have fewer microstates actually are forcing all the particles to be organized together or stay together in the same energy level. So what you can see is that you can start seeing the connection between that idea of disorder with the idea of microstates. So when we say disorder, we really just mean that that is the state that has the most number of microstates, which actually allows them to distribute the particles more widely. Whereas the state with the smaller number of microstates are forcing the particles to be in a specific arrangement, and that is not preferred by the system. Okay, so that's a really important idea I want to get across, keeping in mind that what microstates really is measuring is just ways for molecules to disperse or to distribute their total energy. So when we say we have a lot of microstates, what we're saying is really just the particles have a lot of ways to distribute its total energy.